It's good, yeah? Good possibility. So thank you all for joining our workshop. And this workshop will be fully devoted to AI, influence of AI to mathematics and working mathematicians. And how we decided to organize it. Professor Ruzi Vishna in August sent to our mailing list of our department email where he just told us that two June and July, I think, issues of Bulletin of AMS were fully devoted to this AI and mathematics topic. And that's why we decided to become more educated in this topic, because now I think most of us not so educated. Well, at least me. I hope you may be more. So we decided to organize very fast this workshop. And we want to start with very overview talk of Sergei Gukov. I will introduce him, of course. And after that, something more specific. So about Sergei Gukov. So it was a very long talk. It's the first on August talk. It will be given by Sergei Gukov, director of the American Center for Pure and Applied Mathematics, consulting director of the American Institute of Mathematics, and professor of theoretical physics and mathematics at the California Institute of Technology. And Sergei is highly relevant speaker for our workshop today. And I'm very excited to have him with us. His talk is titled Mathematics and AI Latest Trends and Future. And it would be great if you could ask any questions you may have at the end of his talk. And Sergei promises to address most of them. One word for offline participants. In the case of Syrian, as I understand, we have good shelter downstairs, but it's maybe better to be just in this corridor. It's safe. Uzi told us that this corridor is quite safe. Okay, let's start. Sergei?
Thank you, Lena. It's a pleasure to be here, so thanks for inviting me. In fact, I like the idea of such workshops and interaction, and hope that in future iterations, I can even participate in person one way or the other. So when we started discussing this, Lena gave me a very high toll of overviewing what's happening. She asked me a number of questions, for example, how I personally got into the subject, what got me interested, what was my experience, and how things feel like from mathematician's point of view. So I hope that I'll address some of these questions in this talk. In fact, I'll try to share with you, to the extent reasonable, my personal journey in this the subject, what worked, what didn't, what's hard. And most importantly, I hope that in this talk, I can also share not only how AI can help mathematics, research level mathematics, but also how we can help AI. And this is something maybe for part of the audience who is already familiar with AI. I hope that I prepared a structured talk in such a way that depending on your background, there will be something to take away from it. So in particular, throughout the talk, I will try to give you a gentle introduction to some of the rather technical things in AI. Of course, it's impossible to do it in 1 hour, but I'll try. As I say, I'll also try to have another theme in the talk of what we mathematicians can do for AI today and why it's very timely. So I'm actually most excited about this part, that it's not only AI for mathematics, but the other way around. So I personally was actually not interested in the subject until about 5 years ago. I was doing purely theoretical things by usual paper and pencil methods. And that was already after AlphaGo, and AI, of course, was in the news. So I just decided to start one project on AI and mathematics to try it out, to see how things go. And I was hoping to convince myself that I don't need to learn it because it's probably just a hype and it will pass and not something I need to worry about. So I did the project and luckily, or unluckily, for whatever happened, basically I convinced myself of the opposite, that this is something I need to learn simply because using AI in that work, we managed to achieve 10 times the performance or results I could do with paper and pencil calculations. And so if anything, I realized that for mathematics, AI is a very useful tool. Think about it as super powerful pocket calculator if you want to be very pragmatic. And therefore, I definitely need to study it and if I want to use it. In fact, I believe that going forward, basic AI literacy will be a very useful tool. It's very much like using LaTeX. So of course, using tech is not a formal requirement when we hire professors, but probably you would agree that people who don't know how to type emails or use computers even at the basic level, they're probably disadvantaged compared to the ones who can. And that's how one can view these tools. They're just powerful tools. But another aspect of AI, which is slightly unusual, is that you can't expect me to do, say, 100 times or 1,000 times better as a mathematician tomorrow. So my ability is not really scalable. But one aspect of using AI is that if you have a performance, and actually all the experiments or results that I'm going to share with you today are done on very modest, basically 1 GPU computer. So it's not about resources. So if you manage to demonstrate something useful with small resources, AI is kind of interesting because if you put a little bit more money, basically bring your friends with more laptops, then you can scale the results. So this is actually not something you can easily do just by, I mean, it's true that by bringing together a group of mathematicians, we can get stronger results, but it doesn't scale as quickly. And that's another interesting thing that, first of all, everything I'm going to tell you can be done on very, very small compute resources. And second lesson, at least the way I take it, is that if there is already demonstrated performance on small resources, we don't have to worry about getting a lot of it because there is no stopping point. And therefore, if we can achieve something which is 10 times better, that was my experience back at the time, definitely one can do something 100 times better, 1,000 times better. So that's already good news. So let's see. Let me try to see if I can advance slide. Yeah. So what do I mean? Let me quantify a little bit what I mean by this 10x improvement. So before I came to the subject, I was doing knot theory and quantum invariance. And to me, this transition, if you can call it transition to AI, was actually natural for a number of reasons. So first of all, in my previous career, I like building bridges between different areas of mathematics. So that's also already very natural to build yet another bridge between math and AI. But there is another point, which is what I'm trying to illustrate here, that in knot theory and quantum topology, there is a very long-standing question of producing invariants that would be actually useful for low-dimensional topology. So even though both subjects, quantum topology and low-dimensional topology, have the word topology in it, there are actually very few bridges. And this is a pity, and many of us would like to see these fields much closer. And in topology, low-dimensional topology, there are many outstanding, very well-known questions. For example, smooth Poincare conjecture in dimension 4 is probably one of the most popular. So basically, it's a question whether what looks like a sphere is actually a sphere. And unlike three-dimensional conjecture, which was proved by Perelman, four-dimensional one is interesting because we don't know what the answer is. So we don't know if, we don't even have a guess. So in many conjectures like P versus NP or Riemann hypothesis, we sort of know which way it's going to go. But with smooth Poincare conjecture, opinions are split and we can interpret previous experience either way. So it's actually not clear at present, at least, whether it's true or false. Namely, whether homotopy sphere is necessarily going to be a smooth sphere. So how many exotic structures you have on a four-dimensional sphere. And there are counterexamples to conjectures like smooth Poincare conjecture. Another one due to Ralph Fox is slice ribbon conjecture. It's about property of knots. I'll come back to this later. So there are many such long-standing problems, and they all, even if they originally are formulated in terms of four manifolds or three manifolds, they all can be re-expressed in terms of knots. So using either Kirby calculus or a similar presentation. But the problem is that the kind of knots that they require have a lot of crossings. So there are many potential counterexamples to many of these conjectures, but they usually start with 50, 70 crossings and then quickly go into hundreds. But quantum topologists, including myself, rarely venture outside of 10 crossing territory because computations become really daunting beyond 10 crossings. In fact, even the rare breed of quantum topologists who worked or tried to compute something beyond 10 crossings cannot really penetrate roughly 20 crossing barrier. So number of crossings is a natural kind of usual degree of complexity of knot diagrams. And there are many reasons for this. One is that the number of knots itself is growing exponentially with number of crossings. So if you try to draw a knot diagram, you'll have more and more choices. But also computations of this quantum invariance, they typically require some summation for each crossing in a knot diagram. If you want to compute, say, John's polynomial or other polynomial invariants, they typically involve such sums for every crossing. So therefore, naturally, your complexity grows exponentially. And this is a very important point because even if you assume that technology evolves according to Moore's law, so namely computer power will scale, say, by a factor of 2 every couple of years, it means that if today we could compute 16 crossing knots with a certain compute power and time, in a couple of years, we'll be able to compute 17 crossing knots and so on, because we're plotting one exponential against another exponential, or on a log-log scale, it's going to be linear. And what this means is that if I want to compute something for 100 crossing knots or get in the range of 70, 80 crossings, I have to wait 50 years or 60 years. And this worries me a little bit. I'm not sure I have that time. So therefore, on this log scale, if you want to be in a territory of 70 crossings, we need new tools. And that's how I might convince myself that AI is useful, because it basically gave me power to make bigger steps. So last year, last summer, to be more specific, I joined Silicon Valley-based team, a company that's interested in solving IMO challenge using IMO Olympiad using AI. And this was actually a very smart decision, because shortly after, in the fall of 2023, just a few months after I joined this effort, there was an XTX prize put for this effort, namely $10 million for solving AI, winning gold medal on IMO using AI. And because it's a private company, I can't tell you what we're doing, but what I can tell you is that it looks quite optimistic. So in particular, this is, for example, a graph from Kalshi where people make prediction. What's the likelihood of AI winning gold on IMO before 2026? And as you can see here, the plot is steadily and slowly growing, roughly by 5% every month. So it covers March, April, and May of this year. And if you extrapolate, say, add 5% per every month for another 10 months or so, you quickly get in the range of 100. And what I can tell you is that from my experience and based on, for example, what we're doing and other companies are doing, this is definitely very feasible. So this is just around the corner, in my opinion, that yes, we will see AI winning IMO, getting gold. In fact, probably from several different teams. And it will be quite exciting because different teams use slightly different methods. So it will be fun to compare, discuss, and so on. But this is actually not what my talk is about. So at this point, I want to start differentiating that this is interesting effort, but this will be done. So I want to be a little bit more ambitious in this talk and ask, what about high-level research mathematics? Because you can kind of suspect that Olympiad is possible. For instance, when I was a kid myself, I was doing a lot of Olympiads, and then later in my career, even training for US and Russian team for IMO. And the process was fairly straightforward. So even when I was doing it myself, I remember we got excused from school lessons. And over course of a year, you basically go to this sort of boot camp math problem solving environment camp where we were given lots of problems. And after a while, you see that all these problems, even though they're tricky, naughty, Olympiad type problems, they become repetitive. So you see them many times, and then after a while, you quickly recognize that, oh my gosh, there are only maybe 20 or 50 types of problems. And once you see another one, you quickly realize that, oh, this is similar to the problem I've seen before, and start applying the same technique. So it doesn't, so of course, if you see Olympiad for the very first time, it causes anxiety, stress, but once you see it 1,000 times, it doesn't. It's almost like riding bicycle. So it's very straightforward. So that's exactly actually at a very basic level how AI works, how machine learning works. It learns from experience, from seeing and self-correcting or receiving feedback from human expert. So in that sense, it's actually not surprising that we can get good results on high school level mathematics or even undergraduate mathematics, because there is a lot of training data, lots of textbooks, lots of problems which are solved of a similar caliber. But I want to ask a question, what about high-level research level mathematics? So this is a little tricky, and that's my point, in particular because unlike Olympiad problem or undergraduate mathematics, we actually don't have that many solutions to, say, Riemann hypothesis or problems of a similar type. So if we did, we could just train on them, but we don't. And there are going to be a couple of other challenges associated with research level math, which is what I'll try to emphasize in this talk. When I speak about hard problems in mathematics, there is, of course, no mathematical definition of what hard means. So there are various subjective measures or metrics we can try to put on it. But one sort of metric, which is semi-objective, it's not ideal, but it could be used as a good approximation, is to ask for how many years was the problem open? And then if we try to maximize this metric, we're probably going to make good progress. Again, I'm not trying to say that this is perfect metric, but if we use it, at some point, we will get to problems like Goldbach conjecture, Riemann hypothesis, and many other good open problems. So here I give what may look like a random sample of various long-standing math problems. Some of them I'm actually going to explicitly touch in my talk and try to tackle using AI and share with you my experience. Some of them, of course, remain on a horizon, but again, based even on what I said so far, given that this AI efforts are very scalable, you can probably believe that if we manage to make progress and solve, say, 60-year-old problem that was open for 60 years, then just by scaling this AI models, sooner or later we can reach 100, 150, and so on. So it's just matter of time. Question is, what do we do to solve such conjectures which resisted or problems which resisted direct mathematical efforts for many, many years? So this in some sense will be one of the main messages in the talk. Okay, and by the way, if there are questions, please feel free to post them in chat or ask along the way. I know that we have limited time, but I think there is certainly time for some questions along the way. So yeah, this graph, of course, is not to scale. This illustrates, again, some open problems that I personally would like to tackle. and a number of years they remained open. In my experience, it's actually fun to think about this bridge between AI and mathematics, because in a more traditional way of doing mathematics, it's not that on a daily basis we think about, oh, which long-standing problem we want to solve. But once we, in this sort of bridge between using AI, it actually opens new horizons and allows to make, in that sense, much larger steps. So that's maybe another way to qualitatively describe how it feels to work with AI tools compared to the usual traditional methods. So it basically opens new horizons and allows to make larger steps, which goes well with what I told you before. Okay, so as promised, I'll share kind of several perspectives on the subject, so including some basic introductions to even AI and its area of computer science, which consists of many parts. And among it, it includes machine learning, which is actually the area that I personally, where I started my journey. So it's based on dealing with data, so analyzing data, making decisions based on data, and so on. And then artificial intelligence, compared to machine learning, contains several other areas, which to me always seemed a little bit sort of esoteric or too philosophical. So I thought that probably most of my journey will be in machine learning, and I'll never go to artificial intelligence, which has to do with reasoning, cognition. But surprisingly, I found myself thinking about such questions 5 years down the road, even though my initial goal was just to focus on machine learning. So I'll try to replicate, again, my personal journey in this talk, and first start with machine learning, and then we'll see that we actually naturally come back to questions about reasoning, cognition, and so on. So machine learning is usually divided in 3 basic areas. So they're called supervised learning, unsupervised learning, and reinforcement learning. And supervised learning is all about analyzing labeled data. So basically, you want to learn a function given a bunch of points, roughly speaking. Unsupervised learning involves techniques like clustering and so on, and is about unlabeled data. And reinforcement learning is all about playing games. So it's all about making decisions based on data and interacting with the environment. So a typical example is, for example, this lunar lander, which is a very simple Atari game. Of course, games like chess, Go, and all the progress we hear in the news is regarding AI. Most of it is actually about reinforcement learning. In fact, reinforcement learning is usually considered one of the hardest areas of machine learning. So among the 3, first 2 are quite a bit easier in terms of implementing than reinforcement learning. But this talk actually will focus on the last one, on reinforcement learning, and I'll try to explain why. So when you're playing a game, before we get to the weeds of computer science and so on, it's always good to do some back of the envelope calculations. So just to estimate roughly the hardness of your problem. This actually will go well with us trying to estimate hardness of mathematics that we already touched upon before. So here, you probably would agree that hardness of navigating the maze and making the decisions on the upper left of the picture is much easier than hardness of navigating the maze in the 3-dimensional version to its right, or down on the slide in lower left. So this illustrates that we have to think about, first of all, how many actions we have, what's the action space, how complex is the landscape that we're trying to navigate, and so on. As a sort of prototype or toy model, I encourage you to think throughout the talk as I continue speaking on other things. Basically try to entertain you with this kind of problem. So first version, of course, everybody should be able to solve. So just to think about level of complexity, compute how many paths are there for this mouse to go from start to finish. So let's assume that we're working on a square grid of size n. It can make only two basic moves, either move to the right or move down. And if we are to explore, find a way home, then what's the complexity? For example, how many ways are there to get from A to B? Similarly, if we are considering this problem in a three-dimensional space, there are three basic actions. So action space is now three-dimensional. So again, we can ask how does complexity grow with number of actions we can choose, or how does it scale with n, which is roughly the radius that we want to travel. And you can, of course, extend this and ask the question in d dimensions. And this is usually a good question for many of these reinforcement learning tasks, to do some back of the envelope calculations to estimate how hard your problem is. And we'll come back to this later. Now, an overview or a broad perspective of how AI can interact with mathematics. So this is my personal sort of subdivision of this bridges or interaction between AI and mathematics, and one can classify it in several groups. One is using AI to solve mathematical problems, to either formulate conjectures. So this is actually suitable for this supervised or unsupervised learning, or to prove or disprove theorems or conjectures by finding sequences of steps or finding counterexamples, or actually these are kind of examples that I'll give you in the rest of the talk. So reinforcement learning would be more suitable for this sort of tasks. One can also imagine using mathematics to understand foundations of AI. So in recent years, large language models and other complex AI systems actually work really well, but operate as a black box. And one of the interesting questions is to understand or have explainable AI. There are many methods and algorithms developed using geometry and topology, for example, geometric deep learning, topological data analysis, and so on. They can actually draw on our experience as pure mathematicians to develop tools useful for AI. And another broad area represented here on the lower right part of my slide is using AI to assist automated provers, such as, for example, languages as Isabelle, Coq, Lean. They can close goals by, they're actually designed as essentially coding computer languages, programming languages, but they have the ability of incorporating logical operations and steps that we use in typical proofs. So therefore, formalizing mathematics using these languages is one important area of development where AI can actually make a lot of suggestions and stimulate a lot of progress by basically being either co-pilot or automating the entire process. So these are kind of general areas. And when I gave this talk many years ago, I thought that these three areas, of course, they interact with each other, but they're obviously distinct. Actually, these days, I'm not sure. I don't think there are any serious boundaries. And if you think about hardest challenges in each of these three sort of broad ways where AI interacts with mathematics, in my opinion, hardest challenges are very similar. So that's, again, one of the main themes of this talk, that I'll try to convince you that they're actually not that distinct and even closer than they seem. So for those of you not very familiar with this formalization of mathematics and formal languages, so here is an example. It's Lean, and probably one of the fast developing formal languages where you can formulate many of our proofs. These days they're called informal proofs, even the best ones published in papers. If they're written in natural language, they're informal, and this is the way to formalize them. So this is how they look like, and many simple theorems by now you can find them in MathLib or in other databases or sites. Mathlib is probably one of the largest for Lean, so I encourage you to try it, explore it. It's a lot of fun. You can find many interesting ones. Of course, this is a very serious effort, and using Lean is not easy. So Terry Tao, I believe, at some point mentioned that it takes him seven times more time to prove something in formal language. He's using Lean as opposed to natural language, and I definitely vouch for that. To me personally, Lean does not seem as smooth or fluent, but it is, of course, good and important because once you formalize something, you can be absolutely 100% sure that there are no mistakes, no cases missed. Actually, this is quite interesting because community of people who use Lean know that sometimes from time to time you encounter situations where you thought, according to human reasoning, that everything is perfect and approved, but it actually does not close in Lean, and it encourages us to think about potential gaps. And even in Euclid's elements, one of the anecdotal stories is that one of the elements had two cases, and usually when there are two cases, we say that proof for the second case goes in the same way, but in this case, they were not quite symmetric, and this is important to watch for, and therefore the second case actually did require a separate line of proof. And in practice, this is how the typical screen looks like. So on the left side, you have Lean code. On the right side, you have info view, which tells you the status of the proof. And if you don't see anything red, if you don't see sorries, that means there are some gaps, then your proof is basically complete and verified. So that's how proving in Lean looks like. And I believe other speakers, especially Kevin, probably will tell you more about it. But I just want to illustrate how this third branch of interacting AI with mathematics looks like. Because if you want to assist such automated provers with AI, then basically we have to teach AI how to make right suggestions, right choices. Again, this reminds you probably of decision making that I mentioned earlier, to suggest tactics and steps so that we can close the goal, connect hypothesis of the theorem to the goal. In other words, go from A to B. And this is something that I realized after several years of working in this field that many mathematical problems actually can be formulated in this language, or can be formulated as a problem of going from A to B. In particular, even though I started in areas which are something like knot theory, quantum topology, recently I've been involved in various other projects. For example, in commutative algebra, there is an algebraic version of the Hertz conjecture. So your usual Hertz conjecture is about relation of diameter and dimension and high dimensional polytopes. And that's being solved by Santos, but there are several interesting algebraic incarnations of it on which we recently started work with David Eisenbud and others. And that's completely outside of my usual field. So it's in commutative algebra. And in some sense, the reason I could venture in this field is at the root of it is based on the fact that I mentioned earlier that AI allows you to make larger steps. So in particular, it allows you to think bigger, if you wish, and choose problems from areas that are even less familiar to me by training, but thanks to these tools, we can actually even try questions that normally, as research level mathematicians, we wouldn't try simply because we usually make smaller steps and we have to move much, much slower. So another question, which again was not on my radar a couple of years ago, but more recently we started doing with Kirill Brilyantev and Slava Krushkal is Kazhdan's property T. So that's a question from group theory. And the way it's originally formulated, it's quite non-trivial about unitary dual, but it can be formulated also as a search process. So Azava several years ago proposed the method approach to Kazhdan's property T, where the goal is basically to find a vector in group algebra of our group, a vector that satisfies certain properties. And this is basically a search problem, which again is very suitable for reinforcement learning, whose job is to find a path from A to B. So all of these problems, for example, both of these here listed on the slide, can be easily formulated as a search process, as finding a path which satisfies certain properties. So therefore, conclusion, which is kind of interesting, is that whether you're trying to use AI to assist automated prover, go from hypothesis to the goal, or whether you were trying to prove or disprove many conjectures, in many, many math problems, you can formulate them as a way of going from A to B. So, and that's actually quite interesting, because then from this perspective, many even high-level series research math problems look similar. So the difference, and this is what I'll try to explain in the remaining half of the talk, is that for research level math, this path that we're trying to find is much, much longer than for shorter or similar problems from high school or undergraduate level mathematics. If you think about, again, proving theorem, the ones I showed you have only 10 lines, whereas the Riemann hypothesis probably will have, I don't know, 100,000 lines of lean, or maybe even 1,000,000. So that's going to be the crucial difference. So we'll have to think about how to find such very, very long path. So that's going to be the second part of the talk, but maybe I should pause and see if there are any questions here.
Any question?
Yes, please. Is there a question?
No questions, Sergei.
Okay, very good. So
Yeah.
then I'll just continue.
Everything is clear.
Well, if that's the case, again, it's hard to know the right level at which I should be presenting. I'm slowly ramping it up. But of course, if there are more questions outside of the talk, I'll be happy to discuss in a discussion session in the end of the day. So once we, let me go back to.
Oh, there is one question.
Yes.
Okay, do you see? Is the chat?
It's hard for me to see it since I'm sharing slides, but maybe you can repeat if you don't mind. Read it out.
Of IMO gold medals still 30% even after declined efforts.
Sorry, can you say it again? It says it's about IMO gold medal. What
is the chance of IMO gold medal still 30% even after declined effort? Because
yeah, no, I think yeah. So on that slide, I was sharing the data from April. Yeah, March, April, May, and it was going up by 50%. So by this July, it was probably already at the level of, let's say, 50%. And I think that's very much in line with DeepMind. So yeah, there are many teams which are trying to get there, and many of them have consistent similar results. So that's why my prediction is that next year we'll probably see gold medal by several teams. So yes. So I would say that, again, think about this graph, but also think about the derivative. It's roughly increasing 5% per month. So you can extrapolate what's going to happen. Okay, so right, let me get back to solving these problems. And one of them, so that was actually one of the first projects, to solve the problem, recognize if a knotted diagram, complex knotted diagram, is unknot or not. So basically, we want to decide whether what's shown on the right side of the slide is equal to what's on the left. Okay, And that's fairly easy if diagram is very small, but as I mentioned in the beginning, this is controlled by number of crossings. And if number of crossings gets larger and larger, then it gets harder and harder to decide because complexity grows exponentially. So, but this problem is perfect for reinforcement learning, for this branch of machine learning that's learning how to play games. Because, for instance, in the context of knot theory, there are three basic moves, and they're called Rademeister moves. So actually, the space of actions is not very big. It's very much like an Atari game. You can think of this three Rademeister moves as moves of joystick up, down, left, right. So it's not so many choices that you have in a given state. And complexity should be pretty low. And actually, that's indeed sort of the case. This is kind of game that we try to teach AI with my colleagues. So this was first project listed here. And then by now I did many projects, and here I list three of them, including a recent paper on Andrews-Curtis conjecture that's listed in the bottom. And in the middle is another problem in knot theory, which is aiming to decide whether a given knot is ribbon. So this has important implications to slice ribbon conjecture and to smooth Poincare conjecture in dimension 4. And all of this can be formulated as a game, as trying to connect A to B, for example, complicated knot diagram to unknotted diagram. And they all use roughly three basic moves, like Rademeister moves. So the version which looks for ribbons has one more move of bend attachment. So you would think that it shouldn't be much of a difference because instead of three moves, we now have four. But again, we operate on the same state space, and action space is just four-dimensional instead of three-dimensional. And as you'll see, Andrews-Curtis conjecture is also of the same caliber. It has 3-4 basic moves. I'll come back to it in a second. And its complexity is roughly the same. So 3 years ago, I'd probably predict that all these three problems should be similar. But now I learned that they are not exactly the same. And by the way, on this slide, I illustrate something else, something that I strongly advise all of us to have. I already mentioned that, and this is the point I'm going to make in this talk, that you don't need a lot of resources. This is one of the standard misconceptions that you need a lot of compute power to make progress. This is absolutely not the case. I don't believe that. Yes, it helps to have many GPUs, but everything I'm telling you is done on a single GPU. And that's important because once you demonstrate progress, you can give the code to anyone who has larger resources, and there is no limit of scaling. Second thing that I illustrate here is something I truly believe in, is that we all should share with each other as a community some social residue. So it's good if I leave you with some kind of postcard or some present to play with. And for us, a useful present could be open source code, something that if it works, I can share with you and you can play with it and enjoy it yourself or apply it to your math problems. So all of these projects are completely open source, and I think that's the advantage of doing it with an academic setting. You can go to GitHub, download the code. Usually there is good explanation how to use it. It's usually off the box, kind of it works. And I strongly advise all of us to pursue this interaction between AI and mathematics as open source. Anyway, coming back to this problem, so let me now get a little bit more in details and explain how things work and what you want to do. So you basically train this agent to play a game, and you already see that it's kind of natural to play this game of, say, unknotting, and this is actually what you see. So these are typical graphs that as you train more and more, think again about us playing Olympiad, like bootcamp style problems. With time, you quickly get to some saturation, to a level which quickly approaches 100%. And that's actually good. So this is what you want to see. So these days, when I look at these diagrams and these graphs, I see something completely different. But back in the day, for instance, when we were doing this unknotting project, this is kind of graphs that we saw, and everybody was very happy to celebrate. And as you can see here, the number of crossings can easily go to 40, 50, way beyond what I could do with the human effort. So that illustrates this 10x that I mentioned in the very beginning. So this was actually my first project with my colleagues in AI and knot theory 5 years ago. So another thing that is useful to try is to try use different algorithms and architecture. So this is probably something I won't be able to explain in a short time, but I'll try to the extent possible. That when we try to apply AI or machine learning in this particular context, reinforcement learning, and train the agent to play a game, in this case, unknotting diagrams, it's a good idea to try all possibilities because meaning different algorithms, different architectures, and also sometimes even different ways of encoding the data. Because with all these choices, performance may vary and you want to find the optimal one. So for instance, what this graph shows is reinforcement learning applied to this unknotting problem where different standard algorithms called TRPO, A3C, and they're usually compared to random walker, perform differently. So random walker, of course, doesn't perform very well, and as the length of the braid increases, you see the green dots go down. The orange dots is algorithm called A3C, and it's usually pretty good, but here you can also see that it initially improves up to roughly 50 crossings, but then if you go to the range of 100 crossings, it goes down. But the one which performed consistently better, in fact, that goes to that 100% accuracy is so-called TRPO, Trust Region Policy Optimization. So let me say a few words about these different algorithms. Just to give you sort of reinforcement learning 101 intro. This is actually fairly recent development within AI community, not by AI standards, but by human standards. So many of these things happen within roughly 10-year period. So one of the first algorithms that we would typically use these days, and it's pretty old, again in quotes, goes back to 2013. It's called DQN, that stands for Deep Q Networks. And this is improvement of the traditional not AI algorithm called Q-learning. So Q stands for quality, and the algorithm is simply to evaluate pairs of state action pairs on their quality. So for instance, if this mouse is trying to navigate from upper left in the grid to lower right to find its home, it should avoid punishments and collect energy along the way. So that's a way to collect rewards. So by basically assigning the value to each combination of state and action, you populate this matrix of state action pairs, Q table. Of course, this works if your Q table is reasonable size, but if it's huge, then you need some way to approximate, and that's actually where neural nets enter the picture. So deep Q learning basically achieves this extrapolation even for elements of the Q table that you didn't sample directly. So a bit later in 2016, another interesting algorithm came about, which is quite popular. So this is so-called asynchronous actor-critic algorithm, advantage actor-critic algorithm. And these three words, asynchronous, advantage, and actor, they all start with A, so that's why it's A3C. That's why it's called A3C. And the way it works is that you have several agents. That explains the word asynchronous. They explore the system in parallel, and they report it to, you can say, their big boss, who then tries to evaluate these steps. And there are basically two components in the system. One is actor, that's the one who is making the steps, and then critic is evaluating the result and changing the policy. So that's why this class of algorithms is usually called actor-critic. And there is additional kind of bells and whistles. So here, for example, the way they do it is through the advantage function, which in view of time, I'm not going to explain, but I'll be happy to come back to it. And remember that in the plots I was showing you, this A3C that actually did not perform that well. So it performed well up to 50 crossings, but then if we went to 100 crossings, we needed something else, and that's the algorithm that does really well. So this is called Trust Region Policy Optimization, or as abbreviated TRPO. And again, if I were to explain in one sentence what it does is the following. So many neural nets are based on some kind of gradient descent or gradient ascent. And the problem could be that if your landscape is very rigged, you may make a step in the right direction, but then you can fall and never recover. So these policy methods sometimes carefully avoid this. For example, this trust region policy optimization does the following. So where it defines a region around your state in the space of all possible states, then examines what's the most advantageous move and moves very slowly just within this trust region. And then it iterates the process. So this is quite a bit slower compared to other things I mentioned. In particular, this algorithm is more resource demanding compared to DQN or A3C that I mentioned, but it's actually quite more stable in many contexts and performs better sometimes. But it's a good idea to compare them all. In particular, what we saw is that because so these are some of the off-the-shelf algorithms, and there may be a dozen more that you can find in books on reinforcement learning. But already from this experience, and even from the graph that I shared with you a moment ago, we can learn a very useful lesson. Namely, if I ask you, what's the probability that some off-the-shelf design algorithm, something that we can find in textbooks, will be ideally suited for our hard mathematics problem, the chances are actually zero, because you saw, even in this example of unknotting problem, that some algorithms perform well and some didn't. So that means that in the space of all algorithms, we have these 15 isolated points, which have very special names, such as TRPO, A3C, and so on. But it only is a finite sample of points in the space of all possible algorithms. And for our given hard mathematics problem, most likely, in fact, almost with 100% probability, none of these algorithms are optimal. So something which is optimal probably doesn't even have a name and should be custom designed. So how do we get there? So now we start basically thinking of how doing hard level mathematics can help algorithm development. And this is the last point that I want to enter in this talk, namely what makes math problems hard for reinforcement learning, and how trying to solve these hard math problems can help develop new algorithms. So in this last part, I want to illustrate it with a math problem, which is fairly old. It goes back to 1965, called Andrews-Curtis conjecture. So on the face of it, it's very similar to some of the problems I mentioned earlier, such as playing game to unknot a knot diagram or find ribbons. And it's basically a combinatorial group theory version of such unknotting problems, where you can think of the group presented to you being a fundamental group. And if it's trivial, so you know it's trivial, then the problem is formulated as follows, that you have a balanced presentation. That means that you have some number of generators, let's call them x1, x2, and so on, and some number of relations. And if the number is equal of relations and generators, you call it balanced. And you're asked to do the following, to connect A to B. So again, think about connecting hypothesis to the goal, or finding a path between A and B. So your job in this case is to find a path that connects such balanced presentation to most obvious one, where you introduce a generator and then you immediately kill it by relator, which is basically generator itself. So that presentation could be called trivial. So you ask to do this using only 3 or 4 basic moves. So there are a couple of versions of this Andrews-Curtis conjecture, and there are basically, as you can see, so these moves are written here. There are multiplication of relators. You can conjugate relator by some generators, and there is a stabilization move. That's added. So that's the Andrews-Curtis conjecture from combinatorial group theory from 60 years ago. So it's believed to be false in either version. So again, there are a couple of versions and people believe that it's false. So in this case, unlike smooth Poincare conjecture, we know what to expect. It's fairly easy to just go through examples and try to enumerate them. For example, if you have small number of generators and relations up to certain total length, you can just try to enumerate everything. But then, of course, it stops very quickly because the complexity grows exponentially. So as a result, there are some even easy to write, relatively short presentations that are still standing as potential counterexamples. And some of them come from topology because this problem actually has, the reason it's important is that it has many interactions with low-dimensional topology. For this reason, some of the counterexamples proposed by Salman Akbulut and Rob Kirby about 40 years ago are still standing. And this is actually one area where we recently managed to make progress in this paper I mentioned. And this is also the reason why this combinatorial group theory conjecture interacts with many other open problems in topology, such as this generalized property R, or if you interpret this trivial group, which is part of the assumption in the Andrews-Curtis as fundamental group of a 4-dimensional homotopy sphere, then it actually also interacts with the smooth Poincare conjecture, namely potential counterexample to Andrews-Curtis gives you a potential counterexample to the smooth Poincare conjecture. And that's already quite interesting. So in this recent paper, we managed to solve not the 60-year-old problem, not the Andrews-Curtis conjecture itself, but the important case of this Akbulut-Kirby potential counterexample, showing that it's stably trivial. So basically finding a path of this moves, which takes you from A to B, takes you from given presentation that Akbulut-Kirby gave us, which is very simple, looks very simple, to the trivial one, and it has only 2 generators and 2 relators. So it's again very simple balanced presentation. But a reinforcement learning agent had to find a path which is 1,500 steps. So it's a very long path. And again, in the beginning of the talk, I encourage you to think about the complexity. So namely, what kind of search did it have to do? So the way we code the problem, we have 12 basic moves in each step. And therefore, if you have to go such a long distance, 1,500 steps, then you're basically searching through the space whose size is basically 10 to the 10 with 1,600 zeros. So it's a pretty big step. And in the beginning, when I started describing this class of problems, I said that all of these problems are knotting and Andrews-Curtis should look similar. In fact, they should be much easier than the game of chess. They should be more like Atari games because the moves are much simpler and so on. But actually now we see that it's not quite the case because a typical game of chess, if you play chess, you know this very well, usually lasts about 30-40 moves. You rarely go in game of chess beyond 30-40 moves. And also variance in a length of game of chess is also pretty small. At maximum, you increase by 10x, so by order of magnitude. So for example, longest professional recorded game has only 269 moves. And this was in Belgrade in 1989. So this shows some of the final positions of the board. So the math problem that we're trying to solve in this Andrews-Curtis conjecture is actually like very, very long game of chess. You have to continue a game of chess way beyond what we usually think of typical plays. And this is not just an option. This is not just what happened to us in trying to solve this problem. It's actually necessary because there is a mathematical theorem which says that in this particular problem, Andrews-Curtis conjecture, it's actually quite common to have very short presentations such that there is a guarantee that they can be trivialized. So the path does exist, but there is a lower bound on the number of steps in the path. And that lower bound is hyper-exponential in the length. So for instance, here, this fairly short presentation, which essentially fits in one line of the paper, requires 10 to the 10,000 Andrews-Curtis moves to trivialize it. And again, there are many such. So therefore, the problem we encounter in trying to solve such research level mathematical problems compared to much simpler ones, such as IMO problems or undergraduate level mathematics, is that we're trying to find a path which is like a needle in a haystack, which is very, very long, but it has actually a very disproportionate reward system. So if you find it, you celebrate and you celebrate big. For example, if you find a sequence of many, many steps that connect assumptions in the Riemann hypothesis to the goal, of course, we should give enormous reward to reinforcement learning agent who finds that. And similarly, in many other problems which are open for 60 years, 70 years, and 100 years. But finding such paths, especially if they're long, is a very challenging task, even compared to AI systems which play games like chess and Go, because as I mentioned, in a game of chess, typical number of moves varies between, say, 30 and 300. That's very small variation, just one order of magnitude. Similarly, in a game of Go, the typical number of moves is measured in hundreds. It rarely goes above 1,000 or so. So this basically, again, comes back to where I started, that it's always a good idea to think about complexity landscape, namely, how long of a path do you expect, to give some back of the envelope calculations. And if we teach, so to solve this mathematical problem, so what I described here in my talk is essentially introduction or pre-introduction to this recent paper we wrote, because now what we had to think about is how design new algorithms that can teach AI to make such 1,500 steps that we needed, for example, in solving this particular instance of Agbolt-Kirby counterexamples. Or how do we teach AI to make million steps if you know that, namely, finding this path is extremely challenging because it's like looking for a needle in a haystack. But again, reward system is very disproportionate. And if you think about this, algorithm development that's required to solve such hard, complex problems is actually not very different from questions that we typically start thinking about when we think about, again, reasoning in AI systems and developing what's called artificial general intelligence. That's basically teaching machines how to think way outside of the box, not just close enough to the training set that was used as part of training or work on similar problems that it has seen before, but how can we improve reasonings megaparsecs away from the data that we gave it? So this is exactly the same challenge that we encounter in solving such complex research level problems compared to easy ones. And I want to add with advertisement that at Caltech now we're seeking applications for postdoctoral positions as well as research scientists in this area. So if you like to think about this algorithm development and then hard mathematical problems, please apply. So I want to thank you for your attention, and I'll be happy to answer questions.
Thank you. please answer questions because Sergei is in California now and it's 1 a.m. now in his time zone. So we have like 5-10 minutes. Yeah.
I have one small one. So it seems that your problems are really low on the probabilistic variety, right? I mean, there are not a lot of chance involved. You're almost deterministic. Am I getting this right?
So in terms of mathematics, the problem is in many cases it's so this is another aspect I should mention, that AI, of course, or a neural net is a stochastic system. So it has, yes, whether it finds something or not is probabilistic. So there is also an element of luck involved, but of course we need to optimize and improve its chances to the extent possible.
I understand the algorithms are stochastic. I mean, your problems that you solve, are they deterministic?
Yes. For example, here, I'm not sure I fully understand the question, but usually what happens, and this is point we try to make in many recent papers recently, that, for example, with RL, if you find a solution, you have to formulate problem in such a way that if RL finds a solution, then it's completely deterministic. So then, for instance, here it found the path, and then it's just a mathematical theorem. So that's why it's a theorem. We can present to you explicitly the sequence of moves, which trivializes this Agbulut-Kirby example, for instance. So it is so once something is found, so the process of finding is stochastic, but once it's found something, it's completely deterministic. Same with theorem proving. So for example, you want to go from hypothesis to the goal. If you found the sequence of moves and Lean verifies that it's green, that's good. So.
But however, the algorithms were developed for stochastic environments. For example, Atari has a seed of 255 different scenarios for each game. So actually the agent doesn't know in which game it is located, and therefore it needs to explore. In your cases, I'm not really sure that you actually need to repeat the moves, which most of the reinforcement learning algorithms do.
Well, I'm not sure I fully understand the question, but my point is that all of these math problems, they are like games. So for example, in Atari game, it's exactly the same, or in chess game, your moves or rules of the game are deterministic. Position on the board, you can, at each point, you know where you are, right? So just complexity is huge. So that's all we're exploring. Same with math.
Yes, but your opponent is not deterministic. That's the problem with games. Games are not deterministic because you play for player white and the red player is, you don't know what to do. So you model it as a stochastic environment.
Oh, you mean deterministic in a sense of game theory? Yes, it's not, right? Yeah. In each of these cases, that's another good point. Sorry, thank you for clarifying. Yeah, in each of these cases, we don't know algorithm, and we don't even know if it exists, and we don't know if it's polynomial time if it does exist. Of course, yes, that's a good point. Yeah, thank you. It is not.
And now David Manheim. Yeah, who wants?
Thank you. Thank you for the presentation. Very interesting. I think I followed most of it, though my group theory is not up to following all of it. I had a question though. Your work uses RL directly on the class of problems that you're interested in. And samples, as you noted, are relatively hard to generate, and reward is sparse. I'm wondering what you think about the use of much more general language models that can kind of generalize more broadly, and whether you think that there's a possibility that they do generalize to the point of being able to do research level mathematics just based on kind of their general ability to do more complex things rather than training them specifically for individual problems.
Yeah, thank you. This is a very good question. So I personally have very conservative interaction with language models for several reasons. So one is I emphasize that I find it fun to make progress with just one GPU, which is if we want to use language models, we need something much bigger, more resources, and so on. So that's already one kind of opportunity where I find using RL with single GPU more fun than language model, where we typically don't have that sort of resources to actually set up experiments ourselves. So the best we can do is to use something that others developed or have it not open source, which are not the compromises I'm willing to make. Another reason, actually more serious, so this is just one of many reasons, but another is that language models are really good at translation level tasks, and they're stochastic. So this is actually where stochasticity sort of is a bit of an issue. And I try to use language models even for this kind of problems. For instance, try to learn how to find paths or presentations in this group theory problems or nodding problems, and they're not ideal. So they hallucinate, and most of the time they produce something that's not perfect at all. So again, this is maybe just my personal experience, but I find that they're more suited for problems which can be formulated as translation, and many can. So that's perfectly fine. But the third way to answer this question, and maybe that's the most meaningful one, is the following: that language models are based on overfitting and scaling, and this is something that so the research I described today is in some sense complementary to that. And this hinges on one of the points I made in the very beginning, that how can we contribute to development of AI? So my thinking is that if you find, by thinking about these hard research level math problems, some hacks and tricks how to teach reinforcement learning agents or maybe more general models to think outside of the box, namely they have, I mean, typical off-the-shelf hierarchical algorithms not going to find this needle in the haystack. But if we manage to teach them or develop algorithms, then they can be combined with language models and scaling to produce even something more spectacular. So I view this as a sort of complementary module that hopefully can be married with LLM in the future. So that would be probably most meaningful answer.
Thank you.
And thank you for the question. This is really good question.
So, more questions? Yeah. Okay. Sergei promised maybe to join our panel discussion. But it will be very early in California, so we hope to see you again.
Yeah, I'll be happy to join. I'll get a few hours of sleep, and we'll see you again. So thank you again for coming.
Thank you. Good night. So